Hey everyone, so this week's video is going to be on earthquakes. If any of you guys remember, I actually was planning on going into graduate school for seismology because I wanted to work on probability maps, basically on making them more accurate if possible. I was interested in doing research to see if we could apply knowledge of tectonic plate boundaries and locations to earthquake predictability to make it, to basically take the probability maps that we have now and make them into something closer to earthquake predictability instead. And I'll kind of explain the difference later in this video. But yeah, so this is, I wouldn't say this is my area of expertise because I never did end up going to graduate school for seismology, but this is definitely more my area of special interest. Well, let's just put it that way. So yeah, this week's video, again, is on earthquakes. Basically, we're going to be going over the mechanics of earthquakes, the anatomy of an earthquake, the power that an earthquake has and how that's measured, secondary hazards that are of more concern to us as humans, and the preparedness and modern science of like how we go about, not having earthquakes be as destructive as they could be, or how we try to prevent that anyway. First of all, though, let's just start with the basics. What actually is an earthquake? An earthquake is just, for the purposes of this video, we're just going to define it as the intense shaking of Earth's surface due to movements in Earth's plate, as pertaining to one, event of shaking, that is. And now we're going to talk about what actually causes earthquakes. Anyway, so yeah, what causes earthquakes? We're going to get into the plate tectonics of everything first. So remember how I told you guys that there's like two different ways to look at Earth's layers. You could look at the chemical composition, which is basically, the crust, the mantle, and the core. And that tells you like, how much silica is in each layer, how much iron is in each layer, nickel, all that stuff. And you could also look at physical layers, which is more lithosphere, stenosphere, mesosphere, and that's more about the mechanical behavior of the layers. And what we're interested in and what we're looking at today are the mechanical layers, like the lithosphere and all that stuff. Specifically, we are sticking with the lithosphere for today's discussion. So, just to, recap, there's a solid crust that's sitting atop a hot, nearly solid mantle, and those are the layers which concern us. That's what makes up the lithosphere, is that solid crust and the uppermost stiff upper layer of the mantle that behaves more like a solid. Because the rest of the mantle behaves somewhat similarly to liquid, but it's more considered plastic or ductile behavior. And if you guys want more of an explanation on like plastic versus ductile versus solid, etc., all that other stuff, just let me know in the comments and I'll kind of expand on it. So yeah, that makes up the lithosphere, those stiff upper plates. And it's not really a continuous whole covering of Earth's inner layers. It's more like puzzle pieces floating on top of that viscous mantle. If you want, you can also try to think of it as lily pads on a pond, except, much bigger and more interconnected. Basically, what happens in one lily pad / tectonic plate affects another lily pad / tectonic plate that's connected to it. And so on and so forth, because they're all connected. So what happens in one plate could end up affecting two plates down if they're all connected. Just to keep that in mind, because sometimes there are events where there's like an earthquake in one part of the world, and then somewhat inexplicably for most people, there's randomly a tsunami that doesn't look connected at all. It could actually be connected thanks to tectonic plates. So yeah, now we're going to look at slide 5 for an example of those layers that I was talking about. On the left, chemical, crust, mantle, core, and on the right, the physical, lithosphere, stenosphere, mesosphere, outer core, and inner core. There are, I would say that there's like a theory or several theories that talk about how activity in the liquid outer core might actually be affecting and influencing what's happening as far up as the lithosphere, but I'm not going to get too deep into that. If you're interested, you could definitely look it up. If you want, I could also do a deep dive on that for a future video. And then we're going to look at slide 6 that also looks at the layers. Again, on the left, we have the chemical layers, and on the right, we have the physical layers. I did circle in black the part of the physical layers, or rather, the part of the layers that we're interested in, which are just the uppermost parts. And then slide 7 shows you all the tectonic plates. And remember, the tectonic plates is just how we refer to the pieces of solid crust, plus upper mantle, that we actually feel earthquakes through. Like that kind of produce earthquakes. So yeah, this slide 7, shows all the tectonic plates. The tectonic plates are actually named after, for the most part, what sits directly above it, usually a continent or an ocean. And then slide 8, you can see the tectonic plates again, except, without the name. So you can kind of see more of the shapes of the plates themselves and what sits atop it. For the most part, the plate is bigger than what it's named after, much bigger. You'll never really see a case of like whatever it's named after so big that it covers the entire plate. That's not usually what happens. And now we're going to talk about the elastic rebound theory. So I basically explained the foundation of like what exactly we're looking at. Now we're going to look at what happens there in order to cause earthquakes. So basically, movement really, like the movement of the tectonic plates is not really as neat or as cohesive as the lily pad like analogy might make you think it is. It's more like puzzle pieces moved by strings very awkwardly from below rather than from above, because the thing that's causing the tectonic plates to move is actually the mantle underneath that keeps flowing. So basically the puzzle pieces / tectonic plates are just kind of shifting awkwardly around, and we don't really see any rhyme or reason to it as humans. I'm sure if you believe in God, like I do, you probably think that he's the one deciding all these movements. But generally speaking, we can't really predict how the tectonic plates are going to move. It's a lot less, it's complicated. But yeah, so basically the movements are kind of awkward because the plates are twisting and turning and they're not really fitting neatly together, and they're kind of causing friction as they keep bumping into each other. And that little point friction is what we're going to look at next. As the blocks of rock / the tectonic plates keep bumping into each other, friction builds. Friction is more like a heat and pressure thing. So as the friction increases, the blocks kind of start getting stuck together because there's too much friction for them to keep sliding away from each other. So they just kind of start getting stuck more and more and more as they keep moving together in different points along these. They basically get stuck along fault lines. Like those are the boundaries between the different blocks that they're getting stuck along. But as they're getting stuck on the surface, they're not really, the tectonic plates themselves don't stop moving because of the mantle. And this causes stress and strain to the blocks of rock. Basically, strain is just rocks bending and deforming and stuff like that. And as the stress and strain continues to build, it's actually like storing elastic energy. Eventually, though, the stress will overcome friction and rocks will break and slip along those fault lines. And that basically is what causes an earthquake, because all the energy that's been stored up until that point is released all at once as waves of motion through the surrounding rocks. Hence, an earthquake. And I am planning on making a future video about the types of faults that exist. Like, remember, faults are just basically those boundaries between blocks of rock that are stuck together or slipping together, etc. Because there's like 3 different types of faults 3 major categories of faults that exist, which are normal faults, reverse faults, and strike slip faults. And I can get into that in a future video if you're interested. Now we're going to get into the anatomy of an earthquake. Hopefully you guys understand how earthquakes work now. It's basically just, movement causes slippage eventually. That's the that's the bare bones explanation for it. When it comes to how earthquakes are actually, what's the word I'm looking for? When it comes to how we kind of understand the actual geography and anatomy of an earthquake, there's 2 different things that we're going to be looking at. There's the hypocenter, or the focus, which is the exact point underground where the rock slippage is occurring along that fault line. And then we're also going to be looking at the epicenter, which is just the geographical point on Earth's surface directly above the epicenter. This you would be able to locate on a map. The hypocenter, not so much unless you include depth, and then it's not really the map as we understand it. Usually the epicenter is where you experience the most intense shaking because it's directly above where the slippage occurred. You can actually use math to find the epicenter and the hypocenters of earthquakes. We're just not going to do that in this video because that would be a very involved exercise. If you want me to make a future video on finding the epicenter via triangulation, we definitely can do that. I don't mind walking through that exercise. It's actually kind of fun and interesting. I just didn't think it would fit into a video of this length, or that's more like, because this is supposed to be more of like an overview of everything involving earthquakes, and believe me, it's going to take time to walk through this exercise. But if you're interested, let me know. I don't mind doing that. I can show you guys how to do it. And then in the future, if you ever see earthquakes occurring, you can kind of have fun with it. I mean, not at the expense of the people who suffered, but you can kind of use this exercise as practice for later if you want to find the epicenter of another earthquake that occurs. And now we're moving on to slide 11, which is more about the actual seismic waves. Because contrary to probably popular belief, most people obviously, without, further education on the matter, probably don't know that there's like 4 different types of seismic waves. It's not just one type of seismic wave that's caused by one earthquake. There's 4 different types of seismic waves. The 2 major categories are body or surface waves. Body waves travel through the interior of the earth, while surface waves affect only the surface. Body waves basically consist of 2 different types of waves, P and S waves. P waves, or primary waves, are the fastest seismic waves due to being basically unimpeded by any matter phase. They can go through solid, liquids, and gases. And then there's secondary waves, or S waves, as I already said. These are slower than P waves, and they usually arrive right afterward on a seismogram, and they can really only travel through solid materials, not liquid. So the movement correlated with each type of wave is different. P waves tend to have compressional movement, which is basically pushing and pulling of the ground. And then secondary waves have more shearing movement, which is just kind of sliding like this. Let me put down the paper so I can actually show you. Sliding like this. Compression is more like this, pushing and pulling. And basically, also, the direction of travel for this kind of movement is different as well. Primary waves, the compressional movement is parallel to the direction that the actual seismic wave is traveling. So while the P wave could be traveling, let's say this way, right? Right towards you. Yeah, I'll just do it right towards you. That's the direction the P wave is traveling. And so the compressional movement is doing this along that line. Now, if the wave is traveling this way and it's a secondary wave, the shearing is actually doing this along the line, but in the opposite direction that the wave is traveling. It's perpendicular. And now, surface waves, moving on to slide 12, consist of 2 types as well. These waves, like I said, only travel through Earth's surface. They arrive after body waves on seismograms, and they actually tend to cause the most severe destruction. It's entirely because they are relegated only to the surface. Because they can't go any deeper, they cause the most damage. And basically, as depth increases, as you get deeper, the size of the waves decrease because they can't really do much outside of the surface, further down. But the wave motion itself dies out much slower. So it takes a lot longer for the wave to stop waving, essentially. Especially along the surface, and that's why they cause the most destruction. Not only are they way slower, but they take way longer to die out. So it could feel like the initial earthquake came and went, and then the earthquakes that come after, or as they call it, I think it's called the afterquakes. I don't know exactly what it is. I've heard people refer to it as something specific. I just can't remember. I'm blanking right now. But yeah, those shaky motions that come after the actual big earthquake that occurred, those are the ones that tend to cause the most damage. It feels like the first earthquake came and went, but this one is taking forever. Those probably are the surface waves. And then there's 2 types of surface waves, just like with the body waves. There's L waves and R waves. L waves, the longer name for it is love waves, and it was named after the person who founded it, AEH Love. And the ground moves, in this case, side to side in a horizontal motion perpendicular to wave travel direction. So again, let's say the wave is traveling this way. The ground is moving side to side, kind of perpendicular to that. So while the wave is going this, the ground is moving like this. And then Rayleigh waves, which are R waves, again named after the guy who founded them, Lord Rayleigh. The seismic waves are just basically rolling in elliptical motion in the general direction that the wave is traveling. And so, yeah, they're pretty interesting. Obviously, you never want to... This sort of motion is not something that ground is supposed to make. And that's why it can cause so much destruction, because especially if there's buildings and other structures atop it. Just think in your mind's eye, try to imagine just how bad that would really be. Like, let's say there's buildings and the ground is moving like this. Little mental exercise. Of course, there's slide 13. And now we're going to get into how earthquakes are actually measured. Now that we kind of understand how they operate, how they're formed, why they happen, etc., where they are. Now we understand all that, so now we're going to get into how earthquakes are measured. There's two different ways to measure them. One of the ways is more objective than the other. And the objective way to measure is through magnitude. This is just measuring the total energy released, like from the source. And this is usually done in a log scale called the Richter scale. And it does range from 1 to 9. Each earthquake is assigned one value only. And so that's what makes it objective. It's all numbers. There's only one value. You can't really argue about numbers. Now, the intensity, that in another way to measure it, is more subjective. This measures the impact of seismic waves at different locations. And it measures it via the Mercalli scale. It ranges from 1 to 12. One earthquake can actually be assigned multiple values depending on where the person is that's doing the observing. And so a little more about each scale. The Richter scale, with like from each whole number that you jump up, that's like 32 times more energy being released. And the intensity, like the intensity measurement. Basically, why it's subjective is that it accounts for things like the location of the epicenter from wherever you are. It accounts for the local geology of wherever you are. It also accounts for building constructions in that general area. So if you're in an area that barely has any buildings, the intensity of the earthquake to you might be way less severe than someone who's in the middle of a city with a whole bunch of buildings around them. And so, like I said, it ranges from 1 to 12 in Roman numerals for intensity. And one earthquake can have multiple ratings depending on where you are. I've already said that. And so, yeah. Now we're going to move on to slide 14. This shows you an example of the Richter scale. This graph was actually produced by the USGS. And it basically shows on the left the actual magnitude ranging all the way to 10. And then on the right, it shows you the equivalent energy release in terms of like explosive energy. And then it also shows you in the center of the graph notable earthquakes and notable energy equivalents that, we have like real world examples. And you can take your time looking at that. That's pretty interesting. It shows you like different things that have happened that would kind of equate to the energy being released by specific earthquakes that have happened. For example, the world's largest nuclear test would probably range around an 8 magnitude earthquake. And then Mount St. Helens eruption, which is, wow, Mount St. Helens eruption, talking is hard sometimes apparently, is almost a magnitude 8 earthquake. And then the average tornado is around like a 4, like almost a 5 in terms of magnitude. So yeah, just kind of take a look at that graph. It's pretty interesting. And then there's slide 15, which shows you the modified Mercalli scale for intensity. And again, ranges from 1 to 12 Roman numerals. And it does actually compare on the right to the Richter magnitude scale for what you might feel in terms of intensity for different levels of magnitude. And now we're going to look at secondary hazards. These are the dangers posed by seismic waves to people due to the way seismic waves affect the surface. Basically, these are just the things that can happen due to earthquakes that then pose a danger to us. Obviously, there's ground rupture, which is just exactly what it sounds like. The ground ruptures, like it breaks. There's always the risk of liquefaction as well. If you have a soil that has a lot of water in it, it can behave like a quicksand instead of like solid ground during an earthquake. Then you have landslides, which are just steep slope failures due to seismic activity, causing a whole bunch of debris to come down on anything that's in its way. And tsunamis are kind of similar. They also destroy anything in their way, and that basically happens when megathrust underwater earthquakes basically displace so much water that the water has to go somewhere, and unfortunately there's land in the way. And so now we have slides 17 and 18, which are examples of ground rupture. Slide 17 shows you the 2013 Philippines earthquake rocky wall. It basically was a rocky wall that extended kilometers through farmland that occurred as a result of the 2013 Philippines earthquake. You can kind of see, and that extends kilometers. Just remember that. And then slide 18 shows you the result of a magnitude 7.1 earthquake in Ridgecrest, California. And that shows you a very long ground rupture as well. And now slide 19 shows you liquefaction results. Like basically the liquefaction has already occurred and this is the result. The building is kind of tilted because it started to sink into the ground. And this one was a 1990 earthquake that happened in Japan. The exact picture is featured in the city of Luzon, I believe. Or the town of Luzon, I'm not sure. I'm not really from Japan, so I don't know if it's a town or city, but that's my source. And now slide 20 shows you a landslide, again in Japan. This time it was a 7.3 magnitude earthquake in northeastern Japan that ended up taking out an entire circuit course in Nihonmatsu in the Fukushima region. And slide 21 is just basically what you would expect from a catastrophic tsunami. This one in Sumatra in 2004. That's just to show you all the destruction that can be caused by the secondary hazards that come about because of earthquakes. That's why I showed you guys those images, not just for gratuitous, enjoyment of other people suffering. I'm not sadistic enough to show that side of me in YouTube. And then obviously we're going to move on to, because now that you've seen all the risks that can actually be posed to you, now we're going to move on to what we're trying to do in modern science to prepare people to be able to combat those risks and possibly mitigate them, like minimize as much damage as possible. And that's on slide 22. We have seismometers, obviously. They measure seismic waves below the equipment. And record them as a series of zigzags. These measurements can help scientists determine the time, the location, and the intensity of earthquakes, and they can even provide data about the types of rocks that the seismic waves have traveled through. So it gives you some geological information as well, just about the rocks themselves. Obviously, long after the earthquakes have occurred, or, just when they're no longer an immediate problem, scientists can then look back at this data and figure out what type of bedrock exists in that region, for example. And then we also have early warning systems, which are basically modern sensor networks that detect initial P waves, which allow warnings and alerts to be sent out before the arrival of more destructive S and surface waves. These warning systems can actually buy people as many as minutes of time of preparation and evasion. And evacuation if possible. We don't really know though. I wouldn't risk it if you're not that close to an exit point where you would be safe. And then, of course, you also have probability maps, which I mentioned at the beginning of this video for what I was interested in doing research on. And these basically just are maps that point out where seismic hazards and activity are most likely to occur due to a combination of seismic history in that region, active fault locations, and local soil data, which is especially crucial for things like liquefaction. And these maps are additionally used by engineers to design safer structures and set regional construction standards. The risk posed to the population in that area are very high if construction standards are not followed, which you often see in places where corners were cut, unfortunately. A lot more destruction than was necessary, and then people start, getting lawsuits. Just follow the rules. Don't be lazy. You could get a lot of people killed. Even if you don't care about that, it's going to cost you a lot of money down the line if you get sued, so just keep that in mind. And again, I wanted to mention, probability maps are not the same as predictability maps. They cannot predict earthquakes. They can only tell you where it's most likely to happen. My research was going to be about combining tectonic plate, information and data with currently existing probability maps to see if we could get closer to predicting them. But I now realize, looking back, that may never be possible. I don't know if I can even say that would have been like a worthwhile career choice. It's probably a good thing I went down the baking route instead. Anyway, so let's look at slide 23 now, which shows you two different probability maps. One is of the US and the other one is of Japan on the right. Basically, anything that looks hotter in terms of colors, like red, orange, yellow, those are the areas where seismic hazards are most likely to occur. And the bluer, like cooler regions, blue, green, purple, are least likely to experience an earthquake anytime soon. Just because there's not there's not really a whole lot of earthquake, seismic history in that region already. And the same thing for the Japan list. You'll notice that all of Japan is in the at least yellow region. That's because Japan is along a tectonic plate boundary. So yeah, keep that in mind. The closer you are to tectonic plate boundaries, the more likely you are to experience seismic activity. That's the general rule of thumb. And now, moving on to what exactly you should do in an earthquake. It's from what I've seen, the instructions are pretty simple. Not that they're guaranteed to like give you complete safety, but they'll help so that you're less likely to experience a lot of damage to your person. So it's drop, cover, hold, and do not run outside. I added that myself because I saw a lot of, the general basics is drop, cover, and hold, but I also wanted to add the last one just in case. A lot of people, including myself, for a very long time had the impression that if you're in an earthquake, you should try to get outside and away from, things that could collapse on you. But actually, if you try to run outside, you're putting yourself at more risk because now there's so many other variables to account for that you may not be able to notice in your moment of panic. For example, a building, a power line, a tree, you know what I mean? And what if the building next to you isn't well constructed or it's being messed up by the earthquake shaking thanks to the surface waves and now you've got glass raining on you. You could have metal, other stuff like that falling on you. It's just better to stay inside, even if that seems counterintuitive. But if you're already outside, you need to stay outside because, again, you run the similar risk if you're trying to run inside. You're running towards the buildings and you may not make it before one collapses on you or something else falls on you. So keep that in mind. In general, though, drop, cover, hold. Drop just means lower yourself to better resist the motion of the ground. It prevents you from falling, but it lets you move around if you need to while staying low. The lower you are to the ground, you're basically decreasing. I think it's like you're kind of decreasing surface area from what I remember from my geology programs. I was told this in passing as well. If you stay low to the ground, there's less distance that the motion can travel to destabilize you because all of you is centered around the same area. So basically you're kind of buffering how much of the damage you're feeling and how much of the shaking you're feeling so you can actually continue to move. And then of course cover, you duck under sturdy table or desk, structures like that. And if you don't have shelter nearby, you'll have to use your arms and your hands to try to provide some temporary protection from your head and your neck because those are the most vulnerable areas on your body. You can pretty much recover from a lot of injuries, but there's very low chances of survival or recovery if something happens to your head or your neck. Just keep that in mind. And then of course you hold on to your shelter or your position, covering your head and your neck until the shaking stops. If shaking shifts your shelter around, you're supposed to move with it. That's pretty much it for today, actually. There's not really anything else planned for this video. I do have future videos planned for types of faults, like I mentioned before, and if interested, math-related calculations for slope stability and for epicenter location, if you're interested, again. For today's homework, though, you can just look at some some historic earthquakes, see how much damage was caused. Also, you can look at some probability maps to see if you're at any risk for earthquake, what the probability is, where you are, that type of thing. You can look at different probability maps too because some probability maps have more information and data than others. And some regions in the world have more accurate probability maps than others as well. That's something worth noting. And that being said, if you guys are interested in any of these future videos, do let me know. Drop a comment below. And aside from that, if you have any questions, concerns, comments, also let me know. Until next time, stay curious.